Okay, so just a little bit about the company. Laguna collaborates with healthcare providers, which are insurance companies, health insurance companies. And what we need to know is who are the care members and care managers and members. So the care managers are employees of the insurance company, and usually individuals with some kind of clinical or social experience. And the members are patients recently discharged from the hospital, and this communication between the care manager and the member is done mostly via phone calls. So this is an example for a transcribed conversation. I didn't say that the goal of this conversation is to make sure that the patient complies with the post-hospitalization health plan. And what you see here, the different segmentations are actually the different topics that we tried to find. And each colorful is a different topic. Okay, so the topic can be either regulatory demand or any item from the health plan checklist. And they were all predefined. And just to make things more clear, this is topic 2. It was called recording disclosure, meaning whether the care manager disclosed that the call is being recorded. And topic 6 was whether the member, the patient, asked to opt out from the service. And topic 9, care coordination, is a little more vague and harder to find. And as you can see, none of these topics are data that language models are usually trained on. So this was our challenge, and this is where the journey begins.
Thanks, Lihi. So our data is unique. While obviously textual, it was hardly a typical task in the world of NLP, natural language processing. It was unlabeled, conversational, transcriptional, and de-identified, which means it was intentionally messed with. Now, in machine learning, the easiest way to tackle a problem is to provide a model with some examples and their answers, which are called labels, then let it study with some supervision. But we didn't have these labels. So the task at hand was an unsupervised one, which led us to perform manual labeling of the data ourselves. This has proved a very challenging task because some of the topics were actually quite abstract or subject to interpretations. Some required prior knowledge, and at times it was very difficult to tell where a topic begins and where it ends. If a human reading these conversations struggles so much to perform this task, you can only imagine how difficult it would have been for a computer. And also, manual labeling is extremely time-consuming, which meant we were only able to do it on a small number of conversations. Now, the conversational nature of our data was also a big challenge because most language models were trained on coherent and continuous text, which a conversation is neither. People are hesitating, repeating themselves, correcting themselves, interrupting one another, making small talks, all of which is being transcribed syllable after syllable, which is why we couldn't directly feed it to our models. The two other sources of noise we encountered were a bit more technical. First, being that the conversations were actually transcribed phone calls, the quality of sound, clarity of speech, the ability of the transcribing algorithm all greatly affected the quality of our data. You can see here two examples, a good one where the sound of was correctly identified as an affirmative gesture, and a bad one where seemingly was confused with swimmingly. The second source was the de-identification process, which is required by regulation in order to completely eliminate all identifying and sensitive information from the data, but in actual, injected the data with a lot of irrelevant noise. You can see here two examples where apostrophes were replaced by random names with spacing between the characters. It goes without saying that the quality of the data greatly affect the performance of the model, which is why we had to think creatively, try to reverse engineer all these patterns in the data so we could automatically remove them and maybe at least slightly improve our data.
Okay, So, so let's see how we implemented these data in a model. Our solution was based on a large language model, LLM, called FLAN T5 Large. We needed a model that would be versatile enough to handle multiple NLP tasks like classification and question answering, which are relevant to our case, and also a model that would be able to generalize well across different domains and different topics, different types of text. Also, this model was pretty easy to integrate as it is rather small and can run on both GPU and CPU. And also important, it is open for commercial use, which is relevant in these kind of applications. So how did we use it? Basically, there are two things that are fed into the model. The first one is, of course, the conversations. We take a raw transcript of a conversation. Then we do some pre-processing. This mainly includes restructuring the data in a way that would help the model understand better the conversation, who are the speakers in it, etc. And also it includes cleaning most of the noise that Adir has just mentioned. Then this processed text is split into smaller windows. Now, in our case, we used a sliding window approach where the model goes through the entire text, split into chunks with significant overlap, so it won't lose too much context. The second thing that is fed into the model is the predefined topics, and here we use prompt engineering. A prompt is the input text that conveys instructions to a model. The specific phrasing of these instructions largely affects the quality of the answer that the model provides. And therefore, it is pretty crucial to come up with good prompts. In our case, for each of the topics, for each of the predefined topics, there was its own prompt. And also there was one general prompt to manage all the text and to alternate between the different topic-specific prompts. So these prompts instructed the model to provide an answer with only one digit. 1, if the model identified the topic in the text. 0, if it did not identify the topic in the text. And we also gave it another option, -9, for cases where the model wasn't sure whether the topic was or wasn't in the text. Okay, and to handle all the results of these prompts in a systematic way, we formed this kind of version control like you see here. Okay, so as I said, there are two things that the model receives as input, both the transcripts and the topics. Then the model does its magic, and it provides an output with the classified text windows, where each of these texts has now its own list of predicted topics. The only thing left at this point is to aggregate all these partial lists into one comprehensive list for the entire conversation.
Thanks, Yair. So we classified 15,000 conversations out of almost 5,000 after filtering out all the noisy and short conversations. As the data was unlabeled, evaluating the model was quite tricky because we couldn't just read all the predictions and inside their context in the conversation and decide whether a topic does or does not appear in the text. What we could do was use our knowledge of the data and compare it with the model's predictions. So, for example, we expected topic number 4 to appear in almost every conversation, or topic number 6 to nearly never appear. You can see exactly that in this graph. Topic number 4 indeed had the highest percentage of predicted recordings, and topic number 6 the lowest, which was a good sanity check for us to start with. After that, we randomly selected 150 text windows, which were evenly distributed between topics and labels, and manually tagged them. We treated these unsures as not found, which proved a valid assumption, and got an overall accuracy of 82%, which is a good start for an NLP task. But as Yair explained, every topic got a different prompt. So obviously, we wanted to see the accuracy per topic. This allowed us to find the weak spots for future optimization. And at this point, our knowledge of the data led us to realize that the accuracy doesn't provide the entire picture, and we may need to choose different metrics. So we picked precision and recall, which are a trade-off of one another. And to make things simple, let's look at an example. A care manager is obligated by regulation to state that every conversation is being recorded. For that reason, we must be able to identify every time that this doesn't appear in the text, right? I don't care if I can correctly find this topic. I just want to make sure I never miss if it's not there. This correlates to the recall metric of label 0, which means it would be better to optimize that on the account of precision. For another topic, you can see in the opposite example where optimizing the precision on the account of recall of label 1 was better. And in general, we came up with an optimal strategy for each topic so that given the 4 possible metrics, we could choose a preferred one for each topic in order to truly optimize our model's performance.
Okay, let's take a step back for a moment from the spooky graphs. So along the way, we've tried different models, different approaches. And when we started as a baseline for our models, we used a rule-based approach. Not this one, this one. So in a rule-based approach, we define a set of keywords for that characterizes each of the topics. Then given a text window, the model counts the frequency of these keywords and calculates a score for each of the topics. The topic with the highest score then becomes the class for the entire window. Very simple, but the real challenge in this approach is to come up with the best keywords that characterize well each of these topics. So to do that, we used various strategies. For example, we did data augmentation using ChatGPT to synthesize new conversations with their labels based on existing conversations manually tagged by us. Also, we used some classical NLP and data science techniques like TF-IDF and cosine similarity. And we also used some domain knowledge and our own common sense to find words that seemed relevant to specific topics. But eventually, as you can see from this graph, this approach led to pretty poor results compared to the FLAN T5, to the LLM, with only 21% of total accuracy. And also, when we look at the accuracy per topic, we see that the results are not that good and that the FLAN T5 model wins in all of the topics. So why are we showing you all this? We're showing you this because for some topics, the rule-based approach is still competitive with the LLM. Okay, you can see here, for example, topics number 2 and number 10. So if we could improve the model's performance for these specific topics, we might be able to leverage its advantages over the LLM. And there are some advantages. Mainly, it is much faster to run a rule-based model than an LLM, and it takes much less computing power. So this is important. And this is why eventually we would suggest to develop a hybrid model that integrates both of these models. Such a model, such an approach would use the FLAN T5 model, the LLM, to classify only some of the topics, the more complex one, leaving all the other topics, the simpler ones, to the rule-based approach. So as you can see, the lessons we've learned and the strategies we've developed along the way in this project can eventually serve as a foundation for new models, new methodologies, more refined ones. And this is for the future, maybe. Thank you.